So, everybody sees my slides? Does everybody see this one? Okay, perfect. So, welcome. So we're sorry for the delay. We had just an issue, and thank you very much for all being here in the basically the starting of the Series 5 of the EDT seminar. We are in Series 5. So thank you everyone for joining. And today we're gonna. So I'm just gonna. We have the first talk, and quickly this overview of the schedule that we have been cooking up. We have been planning for the series number 5. Today, we're very honored to receive Bernhard Rumpe, which I'm going to introduce in the next slide for his talk. We also have confirmed talks from Gabriel and Christina in 2 weeks from now. Hans van Geluwe also is confirmed by the end of February, and we are in finalization of 2 other talks in February and March. And hopefully, as it has become a kind of tradition, we'll try to also have a panel discussion with all our speakers of the series. So it's scheduled on the 27th of March. So book it in your calendars. So we are very honored to host our first speaker, Bernhard Rumpe, and he will be talking about model-based software and system engineering for digital twins. So Bernhard Rumpe is full-time professor at RWTH Aachen University in Germany. He's the head of the software engineering chair at RWTH Aachen. His research interests are around applying rigorous and practical software development methods based on adequate modeling technique. He's notably also the editor-in-chief for the International SOSIM Journal since 2002. He's the founder and co-founder of many startups. He's also author and co-author of several books, more than 30 books, notably well-known Agile Modeling with UML, Engineering Modeling Languages, and many other achievements that I didn't have not enough space for this the slide. So we are very honored and very happy to have you as our first speaker, Bernhard. And without any further ado, I will let you share your slides, and the floor is yours.
Yeah, thank you very much, Jamil. Thank you very much for all of you being here and listening to what I would like to share and to discuss with you. I hope you can now see my screen, the right one. Is that
yes,
okay?
We can see it. Yes,
okay,
we can
good.
see it. Perfect.
Great. So I know that you have been discussing on digital twins and related things already for a while. So what I wanted to share with you is slightly the view on how we think how digital twins might be developed, or at least some of the digital twins that we have might be developed in the future. And thank you very much already for the very kind introductions that you gave for me, so I don't have to say much more on this. We are basically coming from the modeling level, from the modeling and the modeling language definition area. One of the core elements that we deal with is Monte-Core as a language workbench, where we developed quite a lot of languages out of that. And we are currently, from that point of view, also looking towards digital twins much more in the recent years, and maybe I'll tell about this history a little bit more later on. This is our definition of digital twin. Of a digital twin. Maybe that's worthwhile looking at, because it's not completely in compliance with the standards definition, or actually the 118 definitions that we looked at so far. We believe that a digital twin has a modeling part. Of course, yeah, we are biased on that. We have models. It has a lot of data in it, so we call that data shadows that collect this data about what the real physical system does, and it provides useful services that have to do something with the physical system. So this is and these services are going both either to the users that look at the system, or back to the original physical system, and maybe even in form of commands that tells the physical system, that basically tells the car what it should do next, or what happens if the car continues to drive forward or whatever. So this is what we think is a useful idea. So the digital twin is actually also some kind of companion of the physical twin, allowing me to collect data and draw useful information out of that, both for the users as well as for the original system itself. So this is what we think is the core definition for this. And that allows me, and let me go forward in this, that allows me to apply this idea of the digital twin or companion in a variety of domains. I guess we already know that there is digital twins can be basically built for everything. And we did, for example, a few things in this direction on energy management in buildings, which is quite interesting today. We started that already a while ago, but today it's pretty interesting to do that, but also for other kinds of systems. When we want to develop this kind of digital twins, interesting question is what is the starting point for developing such a digital twin? And we believe that there is a good idea of saying that physical systems do realize functions. This is coming from systems engineering, from mechanical engineering people, but also from other areas. This idea, this abstract notion of a function, is something that is really a helpful concept that helps us to understand what the physical system is for. And we looked at quite a number of these different physical systems that we have. They all come with this idea that they do some kind of function. Train, for example, cars, medical robots, they all they have some functionality, and that's why they are there. It's not a physical system on its own, but they do have a function, and both the form of the system, how it looks like, and also the geometry, they all follow this idea of that they fulfill their function. And actually this notion of function is can be made pretty precise in terms of a mathematical function if we follow a formalization of what the system actually has to do. And that's we actually once in a while we look into the I have to look at how can I do comments. Yeah, here it is. That's how I can do comments. So we actually once in a while look at mechanical engineering books, and there you find this idea of that a cyber physical system or physical system is actually something which takes input and produces output, very much like the mathematicians do that. And this taking input may be data and signals. This is what we from computer science know pretty well, but it may also be actual physical gadgets like items, screws, things like that, fluids, or energy that comes in continuous quantities, and it's being somehow transformed in other kinds of energy, fluids, items, and other kinds of data and signals emerge. And this is a very universal concept that has not been actually created by us, but by our mechanical engineering colleagues. But we on computer science, and this is why I am so interested in this, we have, at least for the data part, so for the lower part, we do have a theory for that as well. And connecting this theory with the theory that is more on the physical side is something which is pretty interesting for cyber physical systems, and then also for the digital twins that are part of these cyber physical systems or observe these cyber physical systems. A second relevant principle is actually, I don't know how to come to the next slide. It seems my computer has, my computer doesn't like me today.
I think you need to deselect the marking tool and click on the mouse up there.
I hope so. Yes, it does. Interesting. I have to, sorry for this, I have to reselect it and delete. It's not that the case that I didn't do that for a while with my lectures, but I somehow completely lost all my knowledge about it. So I'm back.
There's also an empty screen, but an empty button up there to make it easier to erase.
Yeah. Okay, so here we are with the cyber physical system in various forms, and you see on the right hand side basically that and this is unfortunately a German one that comes from a mechanical engineering book that describes that as energy, material, stuff, and signals as data that is coming in and out. And putting these theories together, there's a number of pretty universal principles in there. Abstraction, for example, is an important principle, allowing to abstract away from unrelevant details like and only looking at the relevant things, like looking at the interfaces, looking at the behavior, which varies over time, at the interactions, but not looking at the internals. That's a very helpful principle in that respects as well. The first thing is that the next thing is that we also need the possibility to describe underspecification, to say that we don't know the very details, but we know a range. For example, that the voltage that has to come in is between, or the energy coming in is between 10 and 20 volt amperes. So then we can deal with it in a useful way. Or on the output side, how the output is related to the input. Is there some kind of Wirkungsgrad, so you use output, so the ratio of the energies that is being lost and all these things. So underspecification is relevant. The next thing is that we need this idea, this notion of that input and output change over time. And this may be either discrete or continuous, or to a large extent continuous, and sometimes it's jumping. So you see this on these two screens, on these two timelines in here. This is a mathematical construct that can be precisely described. And then if we have that as a mathematical structure, we can actually describe the behavior of a cyber physical system as a mathematical structure too, as a function that takes the input and produces output. With all these time delays and storage elements and that completely works. And the next and then most interesting and important, and also for us pretty much interesting principle is, of course, what mathematicians told us. We are able to compose functions and actually also to decompose functions, which means that we, in our case, decompose architecture. Now we are able to have one big blob function and decompose it into several smaller functions, where all the communication is done through these streams of energy, data, and items, and decompose further until we are at elementary functions, which very nicely correspond to elementary behavior, either from the hardware side, from the mechanical side, or to elementary functions on the software side, or to sensors, or to actuators. And that's the elementary elements that we have, and this is it. And the idea, in principle, very feasible, decomposing the overall car in this case, functionally, and also according to the geometry, being then able to compose the results back to a complex working system. So this is all systems engineering. And this is something that is under research at the moment, but also has a lot of progress. To put that together from abstract requirements through a decomposed functional architecture, mapping that to the technical architecture, we are able to come up with a development process for the physical systems. And now comes the interesting point. That's why I told you that. We strongly believe that if we have such a hierarchically decomposed architecture with explicit flows in everything, which is interesting on its own, this is also very interesting to take that as a basis for the definition of a digital twin for my hardware system. And why is that so? Giving these engineering models, we can take them and build sensor collectors. So all the sensing data can be collected and stored in the digital twin. We can build services and further applications on the digital twin that are very much based on this original engineering models. And that has a big advantage, because if I know already where the sensor is located and what I'm sensing there, I have all, say, some metadata available that allows me to make usage out of the data that I'm getting. And if I, so the models, the engineering models suddenly also work as metadata for my collections, which basically means if I have this kind of abstract architectural description of my system, I can put a lot of sensors at the different lines and collect all the data that I'm interested in, which gives me the possibility to come up with digital twins, or a digital twin that knows very much about my car, about my production system, about my airplane. And that's the point that we are trying to investigate further in. Is it completely free to get the digital twin because I already have the engineering models? And the answer is probably not, because at least some work obviously needs to be done. I have to set up the data lake, the services and all these things. A visualization, for example, this is still to be needed, but to some extent, I could do that probably pretty systematically. And our personal belief is that we cannot only do that systematically, we can actually derive a first instance of such a digital twin by more or less automatically reusing the models that we had from engineering. But that's a bold statement that we do at the moment, and we are actually in the investigation trying to find out whether this is really the case, and how we can how much we can actually automate to have digital twins done quickly. Another point looking at this is if I am, and maybe follow me that, so on the bottom left you see an assembly, actually a production line, which has different assets in it, and they have on the physical level, they have just combined them by putting them beneath each other, and then there is someone carrying the working items from one station to the next, and then the station is executed, and then carrying it up from one station to the next. And this kind of modularity on the physical level is also needed on the digital twin level. So on the left, we have, at the beginning, we have 3 digital twins. For each station, there is 1. And when we compose the assembly to one production line, we need also be able to compose the individual twins for the individual gadgets to a larger factory twin. And this is probably true on all kinds of decomposition level for the physical world on the digital twin too. That basically means, ideally, the digital twins are composable and composed in accordance to the physical system composition. So there is a one-to-one correspondence between these things. And we actually tried that to mimic that somehow. Though, if I buy things, I typically buy a physical component together with this digital twin. And that would be, sorry to go back to the picture. So digital twin number 1 corresponds to component 1, and I buy them together. And then I compose that with digital twin 2 and component 2 and 3. So this is not a really completely hierarchical view on that, because there are two dimensions. I have this composition level on the digital twin side, and I have this composition level on the physical side. And but ideally, I can look at this from a parallel on the physical side composition level, and I can also do that on the digital twin level. So this gives me these two possible views on the world. Either only looking at the digital twin because that resides in some kind of background cloud system, something like that, or look at that from a component side, to say component one and its digital twin are deployed together and integrated in my system together. So this is one of the things that we ideally would like to see in our world. And that's basically the same picture again, but I like that one. This is a picture that shows how we, if we do this composition from very low-level elements up to the production platform that goes over several factories, then we start with the engine, put that together on the shop floor, put that together in the factory, and potentially have several factories that work on each other. And actually the top two areas, so from the factory and the networks of factories, SAP, for example, is already active to some extent. But on the more controllable shop floor and engine level, that's more something where this is close to the machines. Here, for example, like if it's a Bosch or Siemens engine, then Bosch and Siemens are more responsible for doing this. However, in total, the overall things have to work together. That's what we show on the middle side. We have all these different digital twins are somehow need to be integratable. And of course, there are solutions, and these solutions need to be integrated in a stable form. Many open challenges, but also some achievements that we see at the moment already. What we believe that these kind of things work better if we, as I mentioned, originally we use models quite a lot. And where are models of interest in that area? We see basically three major areas where explicit models like either UML-like models or domain-specific models or CAD models and all these things can be used. We can either have them very specific, for example, to the application or to the domain that we want to describe. So structural models like that come from SysML or behavioral models, including, for example, activity diagrams or similar things. Or they come from the domain as such, not application or machine specific, but are very much reusable, because they are giving us a standard architecture description and things like that, or standard data structures that are very the same, even though the applications may be different. But those models are typically used at design time. It may also be interesting to use models at runtime. But these are typically models that are specific, so that are to some extent coming from the engineering models, potentially directly engineering models, or sometimes they are somehow extended or augmented to describe the kind of data structures and the kind of system elements that are originating from engineering models, but somehow have been transformed into this kind of models for digital twins. In our experiments, and we do a number of experiments, we usually take data structure like UML class diagrams. We use logic language like OCL that helps us to constrain a few things, but also sometimes to execute, to calculate a few things. We have tagging attached that allows to add additional information, so how to deal with this kind of data, even though in the data model itself that's not represented. The idea of tagging is an extension of what UML, for example, provides with stereotypes. We have because we think, and you see that on the bottom right, we think that this and what I didn't say so much so far is that a digital twin needs some kind of visualization and representation to talk to the users or to allow users to look at things. So this idea of a digital twin cockpit that aggregates all the information in a usable, accessible form is relevant. And generating this kind of cockpit also needs the possibility to describe how the GUI should look like. So we use GUI models in addition, but we to some extent derive these GUI models from the underlying engineering models. Process models are, of course, interesting as well. We didn't look at that so much so far, but I guess this is something to be really helpful. And additional infrastructure, of course, helps. And what we have a tooling that we call MontyGem that actually helps us to really to do this kind of a generation. It generates cockpits, and you see two screens down there, where you on the top right, bottom right, you see an ideal picture of what happens in the. This is coming from a molding engine where you put very hot yellow plastics into the engine, and then the plastic is, while it's cooling down, it's being pressed into the form, and then you get the result, which is some kind of plastics that you wanted to have. And on the left, you see statistical data about that, how often it worked, how well it was, what the quality of the resulting plastics was, what the time temperature was, and things like that. And these kind of things help to understand what the physical production process does at the moment. And how we deal with it, we take all these data models and these GUI models that I already mentioned earlier, push a button, get through the generator and get the digital twin as a data collecting service, and also the cockpit that does the aggregation and does the visualization, more or less not completely generated. I have to say a few words about that as well. More or less generated. This is not completely generated because we don't believe that such a system can be generated fully completely. So we could argue that's a low-code infrastructure, and we actually do that. But to be honest, roughly 50, 60, 70% of the code of that stuff is actually generated. So it's basically the storage, the transportation, the interfaces, and the GUI presentation, the transport to the front end transportation, things like that are generated. But some computable intensive code is not generated. But we add that using an ordinary programming language. We learned that it doesn't really make sense to try to generate everything. Sometimes computational stuff is as best written in an ordinary programming language, because then we can easily test it and can directly include that. We have MontyGem has a bunch of mechanisms that allows to not only do this kind of model-based generation, but also add code where needed. So this kind of extension is helpful. What else should I say about these? We have in the digital twin, we have also this MAPE-K self-adaptive mechanism in there, which allows us to do feedback and control to the users, but we did not collect too much experience with that so far. Where do we use that? We are, this gives me a slightly more possibility to talk about our university. We are in the middle of the second round of what we call excellence process in Germany, where a huge amount of money is spent around the universities, which are able to call themselves excellent. We have, I think, 15 universities here in a variety of areas, and Aachen, where I am in, is one of these universities. And this also includes an excellence cluster with roughly almost 90 researchers for 14 years in total, where we can look at quite a number of things. And the digital twin stuff that we are dealing with at the moment is one of these approaches that specifically we deal with much more. We have a number of AI guys that look at the data and really produce useful things out of this data that we are collecting. And the whole excellence cluster is called Internet of Production, which includes manufacturing processes, even factories that we have in Aachen here under research control. So we can actually look pretty detailed into that data and collect the data and deal with things on that based on reporting of people, diagnostics in the data, and can really learn quite a number of things out of that. On the bottom left, you see actually an area where we have several factories. Actually, our colleagues have several factories where we are collecting this kind of data and trying also to learn between different processes in different factories, what can be used for optimization and so on and so forth. So a big project, and all of them want to know more about their about the processes, about the products, and the digital twins are helpful for these things. Maybe I show you one more thing that we dealt with quite intensively on the last 9 months or so. We have been asked when is actually a company or a product or a group ready to deal with digital twins, or when is the digital twin that they are producing of high quality. And after a while of thinking about that, we have been and we are still working on that, coming up with an idea of a notion of what we call digital twin readiness. So the idea is actually and we are in the middle of this, so I don't want to go too much into these details at the moment, is a maturity model for the digital twin. It tries to come up with at the moment, we are roughly at 30 ingredients, which we are trying to measure. And also a prediction that says which of these ingredients are relevant for the digital twin to be useful for forms of users. So, and here on the right, you see a presentation that says that for only 5 elements of this is the user experience. Does it say it's good or bad? How real-time capable is this thing? Horizontal integration means compositionality to the next digital twins and to the physical twins. How good is it maintainable? Sustainability is, of course, nowadays also an interesting topic, and of course a number of more things. And the interesting point is also that you instead of just saying we need a level 5 sustainability or maintainability level, we also give requirements. It says that the goal is which level to be reachable, and on the other hand is also an assessment how good is the group, or are the digital twins of this group at the moment, which gives us a nice possibility to look at these at the situation, how it is, and what still has to be achieved. And the company that we are dealing with at the moment is also using that for internal arguments for improving or asking the management for additional money, of course, to achieve the situation that the goal is corresponding to the actual situation at the moment. And of course, this is for the operation. You see the top element, but we also do that for development and the production, and try to understand how digital twins can be used there. This is pretty interesting because it gives good insights into the situation, how it is. and it shall be. And we are looking forward to additional publications, and I'm also happy to share that as soon as we have consolidated it enough. And so this is just a teaser for what we are dealing with at the moment to make this digital twins readiness stuff useful, not only within the company, but potentially also for others. So I'm actually already coming towards an end at the moment. To summarize that somehow, the first part where I was discussing about this functional idea, this is something where it can be used in isolation and completely independent of digital twins, and it actually is used in model-based systems engineering quite intensively at the moment. But we also think that this idea of this abstract notion of function-oriented systems engineering is a good way to come down to a system architectural description that I can then in turn use for a description of the digital twin, which gives me the possibility to monitor, to observe the different behaviors of the physical twin and use that as an information in my digital twin to understand and to predict what the future of the physical system will actually be. So the data and the models are basics for the digital twin then. And of course, in this digital twin, I can also use that for prediction. And these kind of predictions are then this word that I did not use at all here so far, but where the digital twins originally came from, for simulations, for real-time capable shorthand simulations that allow me to predict the behavior of my system, maybe only a few minutes, maybe half an hour, or maybe a few days. Summarizing at the end, it's interesting. A lot of things to be done, but also a lot of things that are currently happening. Thank you very much for listening, and I would think then hand over back to Jamel.
Yes, thank you very much, Bernhard, for this nice talk. I would like to invite everyone, if you have any questions, just to either raise the hand or ask it directly. So sure, if you put it in the text in the chat, I can read it as well. So no issue. Maybe in the meantime, I was just so I was interested, as you said, this digital twin readiness, and you said it's not, I mean, it's an ongoing work. But I was just curious, would you suggest this model, if you have an estimator of your digital twin readiness, would you suggest it to be used as early on in the process of building the digital twin, or only after certain point in the process, once you, I don't know,
yeah, that's an interesting point. We discussed that also, first of all, this digital twin readiness stuff is slightly agnostic to the point where in the process we are using it. Of course, it makes sense to early come up with the goals. So that can be done already before the product is being developed. And in between, in the middle, we can then assess the current situation several times. Ideally, my personal view is it would ideally make sense to come up with with the digital twin in parallel, or maybe even earlier than the physical twin. But the digital twin in operation only makes sense when the physical twin is actually there.
Yeah.
So we could wait until we ship the physical twin, the physical part, and ship the digital twin together. Or maybe we even update the software later on. That's, of course, always possible.
Nice. Yeah, nice intake on this. In the meantime, is there any remark, question from the audience? Okay, I see. It's going to be a long question from the chat. So basically, Shane, I don't know if you want to ask yourself the question, feel free. Otherwise, I'm gonna. Would you like to ask? Okay, yeah, go ahead.
So there isn't really a question in there. It's more of an observation.
Yeah.
But what struck me was that there's an underlying assumption in this kind of twin, and it is certainly a twin, but it's an underlying assumption that there is design information known about the system so that we can make a good twin. Whereas in the real world, there are often, for example, significant differences between a system as designed and a system as manufactured, or a system as operated or used, because parts get changed out, or you know, things happen that aren't documented or aren't well understood. So for me, a twin is definitely what you've described, and I appreciate that. I like this talk. It's very interesting, very good. But I believe that it's actually a combination of a number of inputs that are brought together and then used to make a kind of a hybrid model. So the inputs I'm referring to are the design information that we just referred to, which may or may not be complete, but also data, as was mentioned in the digital shadow, but also expertise. So people who have direct insights in the system, and also science. We know from science what works and what doesn't. So we can use physics rules, we can use other inputs to create a better model. That to me is a more kind of complete or representative view of what a twin might be. But I'm curious what your remarks are on that, if you agree or disagree. Or
I fully agree with you, and maybe that's to some extent also part of the maybe from the background. I come from the model-based software and systems engineering area. I'm pretty much interested in using models for these things. So I know that, and I was actually very disappointed when I learned to know that there are many physical systems at the moment where the models that are used to describe the design of the physical systems are not of that quality that we would need. Interestingly, my colleagues from the mechanical engineering side, which by the way do not deal with digital twins, but only with construction and these things, they are very confident that this will change in the future, both for simulation area, but also because the complexity of the system becomes worse and the tools become better. So so this way of designing digital twins from the physical engineering models is something that will become more feasible in the future. This is a strong belief from my side. It will not work. It's a strong belief from my side. It's an assumption. Maybe it will not work for all kind of systems, but in the automotive area, we'll see that at the moment. This is where I'm dealing with quite a lot. And what I know of the airplane industry, they are even further ahead. And in the production area, I don't know. It goes both ways.
I don't want to jump in too much, Bernhard, but I agree with you. But actually, I think, and I don't want to steal a conversation either, but no it's also in certain types of systems, such as cars or airplanes, the level of documentation and record taking is very high for obvious reasons, but also including safety. So that's one of the main reasons for it. Yeah. But even in those circumstances, those systems will exist in a context that is never as well described or as well understood. So if you're driving a car in Sweden, for example, it's a world of difference to driving it in Italy or somewhere else. You will see factors that are important for the twin and understanding the twin that are different from one setting to another.
Yeah, so that would mean that if I want to set up a digital twin on a high level side, let's say the car where it is, and I could actually come up with an engineering model that is built after the car is already there. That's, by the way, very true for buildings. Exactly. The situation is that most of the buildings that we have at the moment are not having useful documentation at all, because there the situation is really heavy. So what they do is, at the moment, they are basically reverse engineering the building, and trying to come up with the floor plans as well as the electrical plans, and in particular the gas and oil and water structure in the building as it is at the moment, or the heating as it is at the moment, and rebuild the models from the already existing physical twin. And then after this element of reverse engineering, there's this idea of adding all the sensors where needed, and then you get your digital twin.
Yeah. I think that'll be more common as a model.
Yeah,
in a wider sense.
Yeah. So these green floor stuff is too much greenfield engineering. That's true.
Okay, thank you.
Thanks. Any other feedback, remark, question?
I had two more.
Go ahead.
If I'm allowed,
please.
because again,
please,
I don't want to be the one doing all the questions.
Please, we still have time.
Again, a slight more of an observation, but one of the other assumptions, and I'm not sure, I want to clarify because I'm not sure, Bernhard, is if, because I agree with you completely, function is essential, the function of the physical system. But I think one of the underlying issues perhaps with the twin is that there's an assumption, and I'm not saying you've made that, I'm just trying to clarify by the way, is that the function of the digital twin should be a very close mapping to the function of the physical system. Because a twin, to me, I draw the analogy, it's like you've got two kids that are twins. If you say to the second child, your job in life is to be like the first one and not to look beyond that a little bit, then somehow we're missing opportunities. So a very practical example is you could design a system, a twin, to represent the functional purpose of a car, so driving and moving whatever down the road. But later in its life, we might like to reuse parts of this or recycle parts of the car for other purposes. But the twin hasn't been designed with that specific function in mind, because it's designed for the function of the car, to drive people from A to B. But there are more purposes, more functions that we could imagine for a digital twin, which again stretches the concept a little bit. And I'm very curious what you think.
Yeah, actually, when we came up with our notion of what we think of the digital twin, the problem is as you said already, is that the digital twin actually doesn't do the same thing as the physical twin. So they are not twins in that sense. The digital twin, to my belief, is more a companion, is someone who is living beneath to the physical twin and observing him and maybe giving him advice or basically commands. But it's not a twin in that sense, that as typical twins are, if they are the same. By the way, when I looked at this notion of digital twin, the word as the digital twin must be an abstraction from the physical one. And the interesting thing is that the definition of the word digital in itself already contains the word abstraction. I looked at the Webster dictionary and okay, I said, okay, abstraction is there. So digital twin is basically the abstraction, but it actually does observe the physical system, and it contains the history and all these kind of things, which the physical system doesn't have. After a while, the car doesn't know where it was, but the digital twin of the car maybe know it. So they are somehow more complementing each other. And I also think that the cyber physical system that I was talking about at the moment, it contains, of course, software as well, but this is not part of the digital twin, or is it? It's not completely sharp, this distinction.
I've seen both.
Yeah.
Mm-hmm.
So maybe both.
Mm-hmm.
And these things have to be sorted out somehow.
Yeah. I think cyber physical systems historically came from embedded software. I think that was the origins of the concept.
Yeah.
But now we're stretching it. So you could, in theory, have a system which is controlled by a twin. So the twin is part of the cyber physical system. And equally, you could have a twin of a system that includes software. So therefore, it's a twin of a software component too. So as ideas, they can kind of jump around a wee bit.
Interesting question, maybe to all the audience that is listening here. Can a software system also have a digital twin? And I don't know, is someone here who wants to answer that? I would have an answer, but that's just an assumption. Nobody here?
I can say one thing. We've got 2 master's students working on this concept.
Okay.
We've got a twin developing. We've got a student. I've got a student. I know the student is a twin, but we've got a student developing a twin of a neural network, and a twin, or another student, sorry, developing a project on a knowledge graph to see if they can be described in a twin. For the reasons that using visualization software, we could perhaps learn other things about those algorithms or about those database systems. So again, it's where you draw the lines, but for me at least, I believe yes is the answer.
Yes, I also think yes. For example, security people also do something like monitoring the physical system in the cloud or wherever, and this is also some kind of digital twin, or also just trying to find out whether the system as such does its fulfill its functionality, and is it quick enough, and all these kind of things. So digital twin of a physical system, of a software system, makes absolutely sense. But the interesting thing is, what is a digital twin of the digital twin then? And here it becomes slightly philosophical.
Yeah, but it's interesting. Thank you.
Yeah, thank you very much for this discussion. And I think our time is almost over. Is that so?
Yeah, we still have 1 minute left, and I was gonna maybe end it with a meta digital twin. I don't know. Meta level. But yeah, feel free when we still have 1 minute if any questions. Otherwise, well, I would like to thank Bernhard first for the talk. Thank you very much, and thank you everyone for being here, for attending. So yeah, I think with that I say have a nice evening, everyone, and see you in 2 weeks.
Bye.
Bye. Ciao, ciao.
Thank you all.
Bye.
Thank you, Bernhard.
Bye, thank you.